Chapter 2, Section 4, one-sided limits. Because really, this section and the next section go together. Up until now, when we talk about limits, what were we talking about? When we take a limit, what do we do? So if I took a limit as x approaches 3 of 2x plus 1, what would you do? Just plug it in. Always, always, always just plug it in, see what works. So that's your limit. And then we discussed something called the epsilon delta proof. Remember that? If I ask you to put it down, could you put it down? What's the epsilon delta proof?
0
Very good.
absolute value x minus
Very good.
and that's I think it's delta
Very good. Because that's the x's.
and 0
What does that arrow mean? Implies. Very good. Very good.
absolute value
Very
x minus delta absolute value less than absolute.
excellent. That's excellent. And remember what all that stuff means? Okay, what this really means here is I said we had a curve. Your x and f of x. This is your in your voluntary your definition of your variables. This deals with the x-axis. This one deals with the y-axis. So we say that at some value in there, if we plug it in our function, this is our c, it will equal some value f of c, which is our limit. So these are the points we're looking at. We're trying to get c. It's within some interval. So what this thing says, we have x minus c is less than some delta. What that means is the delta is the distance between the x value and the c. As that goes to 0, what happens? X becomes what? Yeah, x becomes c, which is what we did. X becomes c, so we just plug it in there. When we plug it in there, it goes inside our function, and that equals our limit. So if we take so this x here corresponds to this f of x. This distance here is our epsilon. So as that goes to 0, what happens? Our y values eventually go to our limit, which is what happens here, as what happened here. So that's what it's saying here. So as we get closer to our c, our y values get closer to our limit. That's what it's supposed to mean. We could do it from both sides. So this distance here is also delta, and it also goes to 0. It goes to here. Here's f of x. It gets closer to our limit. So that's what's happening, our epsilon delta. No matter, here's our c, no matter how close we get to it from either left side or right side, the y values get closer to some limit point. That's what all this stuff's about. But as you just said earlier, let's just take this and plug it in there, see what works. What if we had this function? At x equals 0. Remember, limits do not have to exist to exist. Remember what that means? Limits simply have to approach the same value. We had that example earlier. This is our C value. As x gets closer to C, what happens here? The y values get closer to 4. As x gets closer to C, the y values get closer to 4. So the limit is what? The limit of this function, as x approaches 2, the limit is 4. Even though it doesn't exist there. It simply has to approach the same value. Is that clear so far? Because if not, then doing one side is not going to work. What is this function going to look like? If we graphed it, what would it look like? Work it out. This plot, if you don't know, plot some numbers in there. Put some negatives, put some positives, put some zeros in there. See what happens. Again, this is a math course, not a guess. So if you plot some x's, so when x is -2, what's our value going to be? So x is -2 over absolute value of -2. -2 over 2 is -1. When x is -1, -1 over absolute value of -1 is also -1. At +1, 1 over absolute value of 1 is 1 over 1 is 1. At 2 is 2 over 2, so it's 1. That's how, if you don't know, this is how you're supposed to check. Plug some numbers in there. Don't ever just look at it, think you know what you're talking about. You don't. I mean, nobody does, unless you do this for a whole bunch of years. And that's why I was looking at everybody, see which one of y'all will pick up a piece of paper and a pen and try to figure this out. Always understand what's going on. Plug in some numbers, see what's happening. Now, why did we use 0 as the important point? Because if I was going to put this in an equation, that's how I'd set it. Y at 0. Because C is usually the point where funny things happen. If you put it anywhere else, it's going to be either 1 or -1. At 0, 0 over 0 is what? Is it 1 or is it 0? Or is it undefined? That's a huge discussion. Because we said if 0 is on top, it equals 0, right? If 0 is on the bottom, it's undefined. But how many times is 0 going to 0? I'm not saying this is right or wrong. But it could be 1, it could be 0, or it could be undefined. That's why this is a very special case. And that's why whenever we have that, we always see there's got to be something else we can do. We can factor something out. So we don't want to deal with this. So, since we can't really solve this one just yet, let's look. This whole section here deals with this type of problem. We have a situation where we don't know what happens at the C point. So let's look at what happens on each side separately. So what this is saying, like our epsilon delta proof, you notice when we proved that, we took some values to the left of it and saw how that behaved. Then we took some values to the right of it and saw how that behaved. This is what we're doing. If something funny happens at a value C, what we're really doing is we're taking two separate pictures here. Let's analyze those. These are called one-sided limits. Because what you've been doing so far without knowing it, you were doing two-sided limits. You were looking at approaching the same value from both directions. So on this side, here's C. Let's look at X. Let's look at X like this. This is as X approaches C from the what? From the left. As X approaches C, is the left on a number line, is the left negative or positive? Negative. Because if you remember the number line from elementary school, you have negatives here and positives here. So if it's from the left side, we use the negative symbol. So that's what the symbol there means. This is the one-sided limit. As X approaches C, this is going to be our left-handed limit. Yes. Because we're approaching it from left. Because think of the number line. If this is zero is a number line, that's the middle. We call that this. Let's look at it as our C. What numbers are to the left of it? The negatives. Numbers to the right of it are positive. Now, why? Because how do we notice? How do we calculate the difference between two things? So, the distance between 0 and 2 is how far? Is it positive or negative? How? What formula did you use? Yes. X2 minus X1, like we did in the slope. So we had 2 minus 0 is positive 2. How about negative 2? So it's 0 minus negative 2 is going to be still 2, because distances have no sign. But because we use the negative value inside there, it's to the left of our C value. That's why we use that. Because we have to look at, in order for something to be truly have a limit, it has to approach the same value from both directions. And then the other one, this is as X approaches C from the right. And we denote that as that. And this is a similarity. This is how this section and the next section go together. The limit of a function exists if and only if, which I'm going to start writing as this from now on, IFF. The limit of a function exists if and only if what's true. Yes. The limit as x approaches c from the left is the same number as x approaches c from the right. And this is what the next section uses. If this is true, if the limit value exists, what does that tell us? If the limit to, as x approaches c from the left, if it exists, what do we know about everything to the left of that c value? Do they exist? Do those values exist to the left? Yeah. If it exists, that means that part is continuous. There's no break. Same thing on the right-hand side. If they're both if they both have limit values and they approach the same value, then we say our function is continuous. Because okay, now I'm now actually ironing over both sections 4 and 5. If the limit on the left-hand side exists and the limit on the right-hand side exists, because it means both half of those are continuous and they're both equal, that means they're both approaching the same value, then the whole thing can be connected. And now you have it. Did y'all hear the story about when they built the railroad tracks across the US? They started in California and they started, I think, in Indiana or something like that, Idaho. And then they were going across the country at different directions, from different directions. And then all of a sudden, at one point, they meet. Here's an example. Is the train, how do you know if the train is continuous? If the train tracks are continuous, what can happen? What's going to happen? The train can go from point A to point B without ever falling off. If it's not the same point, like you see, if right here, if the train tracks go there and these tracks go here, do the limits meet the same point? No. Is it continuous? No. Yeah, then it falls off. I just forgot the name of that place. But fortunately, the train tracks didn't line up, which was an amazing feat. And they had the transcontinental train service. So now you can go from one coast to the coast in a matter of days instead of months. You think that's impressive? This happened in the 1800s. Within your lifetime, you guys ever know what the tunnel is? The tunnel. It's a train track going where? Where between where? Yes. Here we have the Eiffel Tower. So that's in where? What city? And then here we have Big Ben, the clock. Where's that? more London. Yep, right here, there's a lot of water. They dug it something like 300 or 400 feet underground, under the ocean, under the sea. So it goes under and it goes under. Now, that's impressive because now they have to be in the same altitude, the same depth, and the same orientation. I mean, this was amazing. And they finally connected. They poked a hole through there and they built train tracks. So they were perfectly lined up with each other. Under the water. I mean, if they were wrong, let's say this group here wasn't either group, if they weren't horizontally level, if they started going up and they hit that, what would happen? Water would gush in there and everybody there would be washed away. So that itself is a more impressive feat. Exactly. I mean, you had so much orienteering. I mean, you had to figure out where exactly are you in a GPS position, and then the depth of it with pressure gauges. So, I mean, we do that. We do that all the time in the space station. You have a rocket going at 16, 17,000 miles an hour, docking with another machine going 16, 17,000 miles an hour, and they have nothing more than a 3-foot circle to try to connect. Once they connect, now you have a continuous path between the two. So there's an example of continuity, is if the limit from the left is the same as the limit from the right, they both meet the same point, then we know it's continuous. So, but we first find both of those separately. And then the next section we'll put the formal definition, but that's pretty much what it is. The limits have to exist, they have to be the same, and they have to be continuous. So let's look at see what kind of examples we have here. Limits at boundary points. Now, oh, yes, the first example we're going to look at, example 1. Here's our example. Here's our function. Square root of 4 minus x squared on the domain -2, 2. Put that bone up. Is it a continuous function from in it within our domain? Why not? Well, no, first off, we said 3 things. When you have a closed interval, you have 3 things to ask. Is it defined, we'll call that A? Is it defined at the endpoints? And is it defined on every point between there? Is there any value inside here that doesn't exist, that makes the whole thing fall apart? What's the rule for radicals, square roots? Right. So the smallest this value here can be is what? 0. Because you cannot have a square root, you cannot have a negative inside a square root. So the smallest inside here can be is 0. So solve this. We have 4, move this over, equals x squared. Square root both sides. So those cancel. Square root of 4 is plus or minus 2 equals x. Plus or minus 2. So we know that there's nothing between there that's going to make it go boom. What does this equation look like? Let's see. Well, to get rid of the square root, if we square both sides, and move the x squared over, so as we add x squared to both sides, this is equation of a circle at 0, 0 with radius 2. Because the equation of a circle is that, which is actually the Pythagorean theorem. Since there's no parentheses around here, we know that h and k are both 0, 0. So it means the center, which is hk, is at 0, 0. R squared equals 4. We square root it, so r equals plus or minus 2. You can't have a negative radius, so r equals 2. The radius is 2. So that's become our graph. It looks like this. It's half a circle. If you can graph the function you're dealing with, it'll help you determine whether a limit exists or not at a point. Which is why I said, let's memorize the library of functions. So we see that at 0, does the function exist? Yeah, at 0, it's 2. If I approach 0 from the left and approach 0 from the right, does it approach the same value? In other words, if I take the limit as x approaches 0 from the left, where does the y value go as x goes to 0? 2. So this one goes to 2. The same thing. If I go to 0 from the right, if I go to 0 from the right, the y values approach 2 as well. So that's not a problem. So all the points within there exist. It's a continuous function between there. So what happens at the endpoints? Since we have a closed interval, you have to look at those values. Can we look at, so here's our graph again. So when c is equal to -2 and when c is equal to 2, we have to take both of those into consideration. Can we take the limit as c approaches -2 from the left? No, because our domain, I could only use the values from -2 to 2. Whereas I can't take it from the left. So all I can do here is as x approaches -2 from the right, what is it approaching? 0. Because remember, I'm looking for the the y value, the limit. As x approaches -2, in other words, as x approaches -2, what are these y values approaching? 0. Now let's look at the other side. As x approaches +2 from the left. I can't take it from the right because that's not in my domain. So as x approaches 2 from the right, what are these values, these y values approaching? So remember what we said earlier. Both endpoints approach the same value, even though it's at two different parts of the world, the limit exists. It's a continuous function. So the limit is 0. Did everybody follow that? Even though, instead of writing from -2 from the right, we had 4 minus x squared. X approaches +2 from the left of square root of 4 minus x squared. If I plug in my values, I get 0, so that's my limit. That was easy. Example 2. We have this graph. Oops. Yeah, that's the graph you guys have. Without running out of sheets. I'll send out the rest of these. I only had 3 copies. But it didn't work this morning. Okay, so for the function graph below, find the limits at x equals 0, 1, 2, 3, and 4. These are my x values. That's the two-sided limit. One-sided left and one-sided right. Let's look at the limits. So what this is saying here is, what is the limit as x approaches 0 of our function? As x approaches 0, what's our function? What's our limit? 1. as x approaches 0 from the left, what's our limit? Bless you. Does not exist. Why doesn't exist? It's out of our domain, right? It's out of our domain. How about one-sided from the right? The limit as x approaches 0 from the right of our function equals what? Yeah, from the right-hand side, as approaches 0, it goes to 1. Limit as x approaches 1 of our function This is a two-sided. Are they going to the same, as it go from here to here, are they approaching the same values? No. This one's going to where? 0. This one's going to 1. So this one doesn't exist. Because they go opposite directions. I mean, two different values. Limit as x approaches 1 from the left. So as it approaches x to the left, what's our value? 0. Because that's where it's going approaching. The limit as x approaches 1 from the right. As x approaches 1 to the right, where is the value going? Yeah, it's going to 1. Limit as x approaches 2. Actually, I'll tell you what, I want you guys to do the rest of those. So the first one. As f of x, as x approaches 2, from the left-hand side, it's approaching 1. From the right-hand side, it approaches 1. So it's 1. This is two-sided. They both have to go to the same point. The limit as x approaches 2 from the left, as x approaches 2 to the left, it's always going to be 1. The limit as x approaches 2 from the right. As x approaches 2 from the right, these get lower and lower and lower. It's approaching 1. Even though it doesn't exist, it's not 1 or 2. It just has to approach that value. That's what limits are all about. Limit as x approaches 3. It looks like it's getting closer, 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 closer to 2. The limit as x approaches 3 from the left. So from the left, it's approaching 2. And as it's approaching 3 from the right, it's approaching 2. Now the limit as x approaches 4 of the function. Can we do a two-sided limit there? Actually, we could. Because it's a closed interval, unless that's an open interval. We can't do that. As x approaches 4 from the left, it's approaching. It's getting closer, 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 closer to 1. And then from the right, we can't do it because it's not in our domain. So that is how it works. If you have a two-sided limit, we just look at it to do both sides approach the same value. One-sided limit, we just look at what's happening on the left side, what's happening on the right-hand side. If they match, that's good. That means it's continuous. We can say it's continuous at that point. At 3, RMC is at 2. Is it continuous at 2? Why not? Right. Because yes, we know that it has to approach the same value from both sides. But does it exist? Is it the same value at that point? So at f of 2, our value is 2. So f of 2, the answer is 2, but the limits all say 1. That means it's not continuous at that point. At f of 3, the answer is 2. And the limits all point to, so it's continuous at that point. That's a, again, I'm running over continuity at the same time. Let's look at the formal definition. Of one sided limits. We have two parts. A. Oh, you have it on your sheets too. Assume the domain of F contains an interval to the right of C. We say that f of x has a right-handed limit at C. Right-hand limit. Right-hand, yeah, right-hand limit. We'll leave it. It's common convention that way. It's a right-hand limit. And we write it this way, the limit as x approaches c from the right of our function is equal to L. Now, here's the important part, because we have to relate it back to our epsilon delta proof. So, no. That's what we're looking at. We're looking at this interval here. Because here's our curve. At f of c, we have a limit. And at f of d, we just have a point. Okay. So we said f of x minus the limit is less than some epsilon. When c is less than it's not zero anymore, so it's absolute value of x. It's not absolute value of x anymore because it's only one-sided. There. Because no matter what we pick, whatever c pick, if we add d or add delta, it's only to the right-hand side. C is the farthest left we can go. So that's that. Remember, in the earlier parts, we had 0 to delta. That's our differences. But now the farthest left we can go is C. All other x values inside there are anywhere from C to C plus delta. And so f of x minus the limit is equal to our epsilon. The other half, this is the right-hand limit. So assume the domain of f contains an interval. Let's use for B or D, B. From B to C. To the left of C, we say that the function f of x has a left side limit at C, and write it this way. The limit as x approaches C from the left of our function is equal to L. And it's got to satisfy this function, this epsilon delta proof. C minus delta is less than x is less than C. So we're going to use this in the next couple of examples. Whenever we prove something algebraically, we have to prove it this way. How big are epsilon and delta? But what do we know about epsilon and delta? Only thing we know for sure is epsilon and delta are greater than 0. And that's the difference. The epsilon This is at C. This is our limit. Epsilon is the difference from our point to the limit. And delta is the distance between our X values and the C point. That makes it limit. We want them to be as arbitrarily small as possible. Because the closer they get, it doesn't have to touch it, just has to get infinitely close to it. All right, so let's look at our first example. Example number 3. Try to use the epsilon delta proof there. Prove the limit as x approaches 0 from the right of square root of x is equal to 0. So we know at 0 it's 0, at 1 it's 1, at 4 it's 2. That's our function. Here's our solution. We know that epsilon has to be positive because it's the distance from our function to the limit. So okay, let's label what we have. We have C is equal to 0. F of x is the square root of x. And our L is 0. And they both have to be positive because they're distances. Distances can never be negative. So let's look what we need. We have f of x minus L is less than epsilon when we want it from the right. From the right, we're looking at from this side. Because the smallest we can go is 0. And that's our C value. So let's plug in what we have. So we have square root of x minus 0 is less than epsilon. When 0 is less than x is less than 0 plus delta. Just plug these values in. So this gives us absolute value of square root of x when 0 is less than x is less than delta. Do we need the absolute value sign around the square root of x? Can that ever be negative? No. So that's redundant, so we don't need it. The whole purpose here is that we're trying to find how epsilon and delta relate to each other. In other words, this one has an x, we need to make this into an x. How do we get rid of the square root on this side? Square both. So x is less than epsilon squared if so what do we notice? We know that epsilon squared is equal to delta. So that's pretty much what it says. We can go back and try to see how this relates, but remember, these are small. So if epsilon is given to us, let's say epsilon equals 0.02, what is delta? In other words, what this thing says is our y values are this close to each other. The limit to the y value is that close. How close is the x value to our c? Zero point zero two squared is what? Because this is 2 times 10 to the negative 2. If we square it, we get 4 times 10 to the negative 4th, which is 0.0004. Okay. What that says is the closer our x values get to our c value, the closer our y values get to the L, the limit. That's what it's telling us. And that's the relationship we're looking for. Example 4. Okay, this one says function exemplified have some kind of limits at each point of interest. In general, that need not be the case. What does that mean? The examples we've looked at so far, at the limit points, they have a special interest points. In other words, if we had 1 over x, we're looking at 0. So typically when we define c, when we look for limit as x approaches c, c is usually not just a regular number. It's a value where the function is usually undefined. So we're looking at now, what if we had this equation? So it has no limit as x approaches 0. From either side. Huh. How would you do that? We have our graph there, you can see it. So what happens as x gets closer to 0 to this function? What's that? Well, let's see what happens to the function. So what do we know here? We have sine of 1 over x. And these are just going to be opposite values of each other. So let's look at this side here. Let's only look at from 0 to 1. Between 0 and 1, what do we know? All points here are fractions. So if we put those in there, sine let's make this a. If x was 1 over a, what do we have there? So as x approaches 0, a goes to infinity. Think of this right. At 1/10, that's pretty small, isn't it? As this number gets closer to 0, that's x. If we divide it, this one becomes 10, this one becomes 100, this one becomes 1,000. So the closer we get to 0, this number gets very, 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 very large. So what do we know about our function? It's asking us to find what again? Show that it has no limit. Why doesn't it have a limit? Does sine of a, what does that go to? It's a sine function. What do we know about sine functions? At 0, it's 0. Sine function is bounded by upper and lower bounds. Doesn't matter how big the angle is. It's still going to be between 0 and 1 and -1. So because it is bounded by 1 and -1, it oscillates between them. So it never reaches a single value. It's either going to be +1 or -1, +1 and -1. That's why there's no limit. Whenever you have an oscillating function, it doesn't have a limit. Cosine is the same way. Yeah. It's unit circle. It's never ends.
Not approaching the 0 on both sides.
As x approaches 0, as x approaches 0, these are my x's. I'm looking at fractions, which is I'm writing now as x is the same thing as 1/a. Because at 1/2, if I put x as 1/2 in there, I get 1/1/2, which is 2. So that's sine of 2. Again, it doesn't matter because it's bounded by 1 and -1. Whatever you put inside here, it doesn't matter how big or how small it is, it's going to be between -1 and +1, always.
It just jumps to 0.
Well, 0 is inside there, but the highest it can go is 1, the lowest it can go is -1, and everything in between there is possible. But if you're looking for a limit, it's either going to be +1 or -1. It could be 0 but again, because of that, it changes between the two. You can't say it's approaching a limit. Oh, yes. Limits. Yes.
Work with all cosine sine functions, or is it specific with this one?
Only sine and cosine because they're oscillating. Everything else are asymptotic. They have for example, tangent has a period, a distinct period where you have asymptotes because you can't have any place where cosine is equal to 0. Cotangent, secant, cosecant, same thing. They all have bounds in which it has to approach. So within those, you can't have infinite many oscillations inside there. So it only works for sine and cosine. Yes, let's look at that. What's the graph of tangent look like? It's sine over cosine. We cannot exist anywhere cosine is equal to 0. Where does cosine equal 0? Pi over 2. And then every pi units from there. So we have asymptotes there. So does it have a limit as x approaches 0? Yeah, it's 0. Does it have a limit as x approaches pi over 2 from the right, from the left? No, it goes to infinity. As x approaches negative pi over 2 from the right, it also goes down to an infinity. So we can't even say in the last one, we can't even say that sine of 1 over x at 0. We can't even say that limit exists, because as it approaches from the left-hand side and the right-hand side, it changes values again. It's an oscillating function. These other ones are not oscillating. Even though they're made up of oscillating functions, they are tamed because we're looking at the ratio of the two. Yes.
So, in the last one, they didn't have a limit because it oscillates or because it was bounded?
It oscillates, and those are the bounds. It's the oscillation that makes it very difficult. Yeah, not because it's bounded. It's just because because, well, if we just had sine over x, can we say, look at that? It's the y values at 0. But it's the sine function itself, as like this, is tame because it's a very smooth curve. Sine of 1 over x, as x gets smaller, this value in here gets larger, and so it changes the amplitude, it changes the period, it changes everything. Not, doesn't change the amplitude, just changes the period and frequency. And that's the review from the trig part. We can go over those if you want to. But review your trig notes for frequency and period definitions. Do the box method. So just by themselves, the sine and cosine function are very tamed. At 0, you can say that they're both approaching the same value at 0. But because we have a function 1 over x that changes very, very violently as it gets smaller and smaller and smaller, because the closer it gets to 0, the larger this value becomes. The larger that value becomes, the faster it oscillates. Yeah, but that's the big problem. If it flips, then we can't really predict what's going to happen. Yeah, and that's the problem. So there's a difference between sine of 1 over x and sine x. It's how fast it oscillates. This one is really quick. This one is very tame. Well, this one, as you saw from the picture, the closer you get to 0, the faster the oscillations. So that's the big problem. That's a good, very good question you had there. Is it always with sine and cosine? No, because sine and cosine themselves are very tame. It's just that if we look at rational arguments, the inputs, the arguments, because this value changes, the smaller it gets, the bigger it gets. The smaller x becomes, closer it gets to zero, the bigger 1 over x becomes. So it changes the speed of oscillation, which is why graphs are very important. If something is, you saw like a Geiger counter, you see something. What we have here, a Geiger counter, if you stretch out a piece of paper, you'd have a sine or a cosine. You'd have a very passive movement of noises of the earth. But we get closer to an earthquake, what happens? It's just, you can't tell what's going to happen. At any 1 second, you can't tell what happens. So that's the problem. Very good question, Ashton. What's up about that? Now let's get back to this. Limits involving sine x over x. And if you want the proof of this, I could send it to you. Talk about that class, with class. But the proof of this, we use the squeeze theorem to find two values that are above and below this one. And then we get closer, we minimize it to see exactly what it approaches. Basically, what I'm saying here is this: whenever you have the limit as x approaches 0 of sine x over x, the answer is going to be 1. And it's not because, well, if you plug in 0, you get 0 over 0. And earlier we talked about, like, we can use L'Hopital's rule, or we can use algebra to fix it. The algebra we use here is the squeeze theorem, is the sandwich theorem or the squeeze theorem. But we take a function we know that's less than this one and a larger one, and as x approaches 0, eventually we get to x equals 0. This value will be 1, this value will be 1, which means that sine x over x has to be equal to 1. For example, if I put cosine x here, is it true cosine x has to be less than or equal to 1? Yeah, because the highest cosine can be is positive 1, everything else is down to negative 1. So that's a true statement. Same thing with sine. It's a ratio. So the largest it could be is 1. The lowest it could be is 0 or negative 1. Since these at x equals 0, since 1 and 1, that means that sine x over x equals 1 as x goes to 0. And the graph itself, you can see there, it starts off small, then it gets bigger, and it dampens again. It's an open circle there at 1. Let's look at an example. Example 5. Show the limit as y approaches 0 of cosine y over y is 0, and that the limit as x approaches 0 of sine 2x over 5x is equal to 2 over 5. What was the first one? It was 0. As y approaches 0 of cosine y over y is equal to 0. Again, here you'd have to use your cheat sheet. If we just plug in 0, we get 1 over 0, which doesn't work. It's undefined. So what do we have to use? We have to use one of the identities or one of the functions in trigonometry. For example, see that? Yes. So let's look at one of the angles. Let's look at the half angle formula. What does it tell us about cosine? Using the half angle formula, we get cosine of y is equal to 1 minus 2 sine squared of y over 2. So as we look at our equation, we know that equals oh, let me going back to here. Because the limit of 1 becomes what? The limit of a constant equals what? Remember the rules, the properties? The limit of a constant is the constant. Because if it's a constant, it's a horizontal line. As x approaches any value, it's that horizontal line. So I'll get that over there. Now, yeah, let's take the limit of this function. Limit of y equals 0 of cosine y minus 1. On the right-hand side, the constant term goes out in front. I should put Let's write x equal that. So it's limit of 2 sine squared of x. That make it much easier to write. Got the dividing by y part. Okay. 2 over y sine squared x. Since x is y over 2, 1 over x is 2 over y. So this is the limit of 1 over x sine squared x. Negative the limit of sine squared x over x as x approaches 0. So this can be written as sine x over x times sine x. I have this one times this one. From our theorem, we know that this equals 1. So negative, and the limit of sine x as x goes to 1, or x goes to 0, equals 0. All that for nothing. And yeah, that's what we're supposed to prove. Now let's prove this one. This has to do with basic trig factoring problems. So this one is B. The limit as x approaches 0 of sine 2x over 5x. We have to prove that it equals 2 over 5. So what do we got to do here first? These coefficients, because if we got rid of those coefficients, what would happen? Then we have sine x over x, which is 1. So that's what we have to do. We have to get rid of our coefficients. So we have limit as x approaches 0 sine 2x. Anybody have their cheat sheet? That's one. that. I'm looking for the double angle formulas. Okay. So sine 2x to sine x cosine x. So that can be written as 2 sine x cosine x over 5x. I'm sorry. So this is from the cheat sheet. This is the double angle. Because 2 and 5 are constants and they're coefficients, I could bring them out in front. I could split these up. Of sine x over x times cosine x. The limit as x approaches 0 of sine x over x times the limit as x approaches 0 of cosine x. What is the limit of sine x over x? 1. What is the limit of cosine of x as x goes to 0? Also 1. So it's 2 over 5 times 1 times 1. Okay. Let's look at number 6 real quick. And the beautiful thing is there's not one right. As long as you follow the rules of math, you can use whatever method you want. So the objective here is whenever you have a sign with an x or a trig function with an x side there, to make sure try to get to sine x over x because that'll make it equal to 1. As long as the limit value of x goes to 0. Example 6. Find the limit. Instead of t, I'm going to use x because my t's look awful. Tangent x secant 2x over 3x. So what do you think I do first? I have a constant here and there's a 1 here. I could take out the 1/3 and put it out in front. Get everything to sine and cosine. Secant is 1 over cosine 2x over x. So this is as x goes to 0, sine x over cosine x times 1 over cosine 2x times 1 over x. Because I have this divided by that, I flip it. Whenever you have a fraction over another fraction, leave the top alone and flip the bottom. X is x over 1, so I flip it. So I could rearrange these as I want to. So I have sine x over x, 1 over cosine, and 1 over cosine 2x. The limit as x goes 0 of sine x over x is what? 1. 1 over cosine. Cosine of 0 is, so this becomes 1. Same thing here. 2 times 0 is 0. Cosine of 0 is 1. So the answer is 1/3. What part? Here? Well, commutativity says once I take, okay, I took this, these are both fractions. That's a over b, but that's the whole thing. X is x over 1. So I take the top, leave it alone, and flip the bottom. So it becomes 1 over x. And then from there, I can rearrange them. I'll put the sine over x, 1 over cosine, 1 over cosine 2x. What's that? Commutativity. I can move around any of these fractions, any arrangement I want to, because by commutativity property, x times y is y times x. So I move the x, so it's x times cosine 2x. So the sine over 2x, the sine over x. The commutativity property. The commutative property of multiplication. The commutative property says that x times y is y times x. As long as they're multiplied, you can move them around how you want to. Works also with addition. That's the reason I start off every semester with going over the rules of algebra. Because it all boils down, I don't care if it's calculus 3, differential equations, whatever. It all boils down to the same stuff, same rules of algebra. And the last one. Example 7. Show that for I'm sorry? That's the limit, yeah, because everything else was 1. So it's times the coefficient. Yes, 1 over 3 is the limit. I know, all that stuff. You just forget about the coefficient. Yes. Show that for non-zero constants A and B do not equal 0. We have the limit as x approaches 0 of sine bx and sine ax equals a over b. Here's, we're gonna take some more rules of algebra. We're gonna make it fit to how we want it to work. So the limit as x approaches 0 of sine ax over sine bx is the same thing as the limit we have sine ax times 1 over sine bx. So far, so good. I need to separate those. Now, I got to make both of these into common fractions. So for this first one, I want sine ax over ax. So I multiply by ax over ax. And this next one, I multiply by bx over bx. Limit as x approaches 0 of we have ax times sine ax over ax, bx over bx sine bx. Ax times sine ax over ax, 1 over bx times bx sine over bx. I'm just rearranging these things because I want to get these guys together. I have ax times 1 over bx sine ax over ax, bx over sine bx. So now, as x goes to 0, well, can we simplify any of this stuff? In this first parenthesis, can anything cancel? The x's. What happens to sine ax over ax? It goes to 1. Same thing here. The reciprocal of it also works. So the answer becomes A over B. Yes, it feels great when math works. If it doesn't, back to the drawing board. But yes, you're gonna see and you're gonna appreciate the sine x over x. Because we're gonna see a lot of that happening in this course. It's amazing how many times you'll see it occur doing just regular equations. Okay, that does it for this half of the day. Today's what? Tuesday. Yeah, we'll finish up the continuity part. Continuity part, we've already done a lot of it. We discussed the concepts of it. We just have to now work on the examples. So we'll do that next time. And I think there are 6 sections in this chapter. If there are 6 sections, we're going to do both of them next time. We'll try to finish up chapter 2 this week.
That's it.
That's in chapter 2.4, right?